The special theory of relativity, proposed by Albert Einstein in 1905, fundamentally changed our understanding of space and time. It is based on two postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light is the same for all observers regardless of the motion of the light source. These postulates have significant implications on the nature of space and time, such as time dilation, length contraction, and the equivalence of mass and energy, E=mc². It has been confirmed through experiments, making it a crucial part of our understanding of the universe. It is important to understand the special theory of relativity in order to comprehend the nature of space and time. The two postulates of the special theory of relativity have several implications that fundamentally change our understanding of space and time. One of the most important implications is time dilation, which states that time appears to move more slowly for an observer who is moving at a high speed. This is because the laws of physics are the same for all observers in uniform motion, and as an observer's speed increases, time appears to move more slowly for them. Another implication is length contraction, which states that objects appear to be shorter to an observer who is moving at a high speed. This is because the laws of physics are the same for all observers in uniform motion, and as an observer's speed increases, objects appear to be shorter to them. The third most important implication of the special theory of relativity is the equivalence of mass and energy, famously known as E=mc². This equation tells us that mass and energy are just different forms of the same thing. The letter E represents energy, m represents mass, and c represents the speed of light. This equation tells us that a small amount of mass can be converted into a huge amount of energy. This is why nuclear power plants can produce such a large amount of energy from a small amount of fuel. This equation is a consequence of the second postulate of the special theory of relativity, that the speed of light is always the same for all observers, regardless of the motion of the light source. The special theory of relativity has been confirmed through various experiments over the years. Some of the most famous experiments include: Number 1. The muon decay experiment. This experiment, performed in the 1940s, confirmed that time dilation occurs as predicted by the special theory of relativity. In this experiment, scientists observed that muons, which are subatomic particles, lasted longer when they were moving at high speeds than they did when they were at rest. This is exactly what the special theory of relativity predicted. Number 2. The Kennedy-Thorndike experiment. This experiment, performed in the 1930s, confirmed that the speed of light is the same for all observers, regardless of the motion of the light source. In this experiment, scientists observed that the speed of light was the same in all directions, regardless of the motion of the Earth. Number 3. The Ives-Stilwell experiment. This experiment, performed in the 1920s, confirmed that length contraction occurs as predicted by the special theory of relativity. In this experiment, scientists observed that the wavelength of light changed when it was moving at high speeds, which is exactly what the special theory of relativity predicted. Number 4. The Haffel-Keating experiment. This experiment, performed in the 1970s, confirmed the time dilation effect predicted by the special theory of relativity. The scientists used atomic clocks placed on commercial airliners and flew them around the world in opposite directions and then compared the clocks. The difference in time observed was in agreement with the predictions of the special theory of relativity. Number 5. The Pound-Rebka experiment. This experiment, performed in the 1960s, confirmed the gravitational redshift of light as predicted by the general theory of relativity. The scientists used gamma rays and observed that the energy of the gamma rays decreased as they climbed up a tower. This was due to the effect of gravity on the light, which was predicted by general theory of relativity. In conclusion, the special theory of relativity is one of the most important theories in physics. It fundamentally changed our understanding of space and time and has been confirmed through various experiments. The postulates of the theory and its implications such as time dilation, length contraction, and the equivalence of mass and energy, E=mc², are crucial to understanding the nature of the universe. Be sure to check out the links in the description for more information and resources on the special theory of relativity. Thank you for watching.